Hello, I'll be presenting two papers of the Euclid reference paper release. The first is number 3, the NISP Instrument, and the second is number 4, the NISP Calibration Unit. Together, these two papers are references for the overall functionality, capabilities, limits, and possibilities of the NISP near-infrared spectrometer and photometer. They also provide an insight and description of the calibration approach, so how we go from values in data files to actual physical parameters that were observed on the sky. My name is Knud Jahnke. I'm an astrophysicist at the Max Planck Institute for Astronomy in Heidelberg, Germany, and I'm one of the coordinators of the NISP overview paper, as well as one of the lead authors of the NISP Calibration Unit paper. I represent the whole team of NISP that has been sketching out ideas for NISP, that has been designing the instrument and eventually building it over more than a decade. The NISP overview paper is aimed at astronomers who would like to understand the overall makeup of NISP, its functionalities, also the requirements, the science requirements that NISP was designed and built on, as well as the limits that NISP has in its operation. NISP has two different science channels. One is a spectroscopy mode, meaning for every pixel on the sky that Euclid can see at a given point, we are creating a near-infrared spectrum, meaning we stretch the light along its wavelength and provide an insight into the spectral energy distribution for each object in the field. The second channel is the photometry mode, think images, where we have 3 different bandpass filters to selectively pass certain wavelength intervals in the near-infrared to the NISP detector system. These instrumental operations lead to data files that need to be calibrated, meaning we need to take out all the specifics of instrumental effects of inhomogeneous illumination, of detector noises into account, and need to calibrate so that we can, in the end, associate a certain value in a calibrated image with a certain physical parameter on the sky, for example, a brightness or a position. To facilitate this, the second paper, the NISP Calibration Unit paper, describes the design and functionality of a NISP calibration lamp that has been built to be able to calibrate detector properties in flight, in space. This lamp is based on light-emitting diodes, and we describe how we came to these design decisions to, for the first time, fly with light-emitting diodes as a light source, and how these are used to calibrate detector properties. NISP performance in space is exceptional. It's better even than we had expected from the ground before launch, and I'm personally very happy about this, and I'm looking very much forward to using the NISP data and also this data for my own science, which in this case is not cosmology, which is the core science of Euclid, but is quasars, supermassive black holes, and their development and formation over cosmic time. I'm very happy that NISP is functioning so well, that it has started the survey over 1/3 of the sky, and that we will be seeing also quasar results very soon.